I don't know if this is working. Oh, okay. So thank you. I will be presenting Nancy. So as the title suggests, this is a library for network calculus. It was recently released as open source and cross-platform. It's written in C# and its main design goals are to be easy to use, meaning that you can easily translate your mathematical expressions into code and run it, and to be parallel, efficient, and scalable, meaning that it can exploit the multi-core systems that are basically everything you can buy today. Also, it is designed to be easy to use and useful for teaching, research, and applications, so a broad spectrum of purposes. It is also flexible and unrestrictive, since it's based on the ultimately pseudo-periodic model for functions, but I will talk about these details later. I would like to start first with examples to give you an idea of why it should interest you. So in the first example, the first thing I noticed that the slide looks wrong. I guess I used a font that is not on this PC, so maybe next example will look a little weird, but I will make it clear anyway. So again, the first example is that we instantiate some simple curves and plot them. So in this view is actually something you can, I of course adapted it for slides, but it's what you can get using notebooks. .NET notebooks are an easy to use environment where you can just write your code and see it running, as this video also shows. So, which is not autoplaying for some reason. Can I? Okay, so anyway, this video was supposed to show that you just press the arrow. Sorry, wrong button. You're supposed to press the button up here and you'll just show the figure on the previous slide. But we can, of course, other than just plot them, we can compute something interesting, for example, the usual horizontal deviation, as in this case, or their convolution, which again is a curve that we can plot. Of course, these computations are simple because we're using simple curves, but we can use also more complicated examples. And in the following, I will use some expressions from literature to show how they easily map into code. So this is a FIFO residual service curve, and here is the code that directly maps it. So I expect this, yes, to look weird. But what's happening here is that I want to underline this convolution operation that directly implements this convolution up here between alpha and delta theta. Then we have the subtraction between beta and the result of the previous operation. Also note the non-negative parameter help us get the positive part as highlighted in the equation. And then we have finally the minimum. So with this code, we directly implement the expression, and then we can easily plot them with given the sample parameters that I have up here. The following example is then, oh yeah, first we can also pretend we don't know anything about this function that we're seeing and test some properties about it. For example, if it's continuous, but also if it's only partially left continuous or right continuous. As we can see, it's true for the former, false for the latter, but also some more complicated properties like subadditivity and superadditivity. We can also check get what is the initial latency, since it's common for many curves in practice to have an initial latency. And then we can compute the value of the curve at or near a given point in time. Then in the next example, it's a little more complicated and I guess hard to read given the font. But here I will not go into the detail of the math, but again, only showing the interesting mappings. So in the first case, we have that the first interesting one is that here, this new function is being delayed by this value, and we can easily get the same using the delay by method, again with the same psi value that is computed with an implementation that I omitted here for clarity. Then we have the summation that here is simply obtained by constructing a list of curves objects, and then a single call to curve data addition will compute the entire summation and give us the result. And lastly, there is also the composition that is also conveniently implemented, and it basically works transparently to the user, since we can just write this code on the left, not knowing how it is implemented, and get the result here highlighted, here shown. So hoping that I got your interest, next I will show the boring part, that is all the list of details. We have that it's a .NET library written in C#. This means that you can use it not just for notebooks as I've shown, but for everything from console applications to user interfaces and web services. Of course, using notebooks, it's also useful for teaching, research, and presentations. And being open source with a permissive license, you can also work on it yourself and adjust it to your needs. It implements min and max plus operations for ultimately pseudo-periodic, piecewise affine, rational to rational functions. The main interesting property is the first one. Where is the, okay. The first one, which means that starting from a given point, capital T, the function repeats its behavior periodically with some static gain C. In this case, the parameters are so, and the periodic shape are so that the function is continuous, but both left continuous and right continuous function can be represented this way. So the library does not get in your way from the perspective of modeling. And it also provides a rich API with the intention to allow you to get to work on your models with minimal additional work. So the list goes from minimum to maximum to addition and subtraction, convolution and deconvolution, both in the min plus and max plus sense. We can compute vertical and horizontal deviation, again, for any kind of UPP curves. We are not limited to convex or concave. And we can use lower and upper pseudo-inverse that have been used in literature to switch from the min plus to the max plus representation, for example. We can compute the sub and super additive closure, and we can do compute decomposition. And finally, all of these come with many overloads for ease of use and optimization. One example I've shown is the addition that, of course, supports both having two operands, but also a list of operands, and do it in a single call. The rich API also includes many methods and properties, many of which I already shown. Computing the value at or near a point in time, checking for continuity, for convexity or concavity, subadditivity or superadditivity, but also some common modification that we may often do with curves. For example, the shifting over the time axis, delay by shifts forward, anticipates shifts backwards. while vertical shift is just a single call to switch over the y-axis. And then cut gives you the view of a function of a finite interval, and many more that you may look for based on your needs. It is designed to scale. As I mentioned, the parallel aspect that I mentioned shows up in two ways. First, most of its methods are implemented to exploit multi-core processors by splitting work over multiple threads. But also the design of objects and methods allows you to write your own parallel code safely, since there will be no problem of interference between multiple threads. And it's also designed to exploit transparently to the user many performance optimization that are mainly based on the mathematical properties of the operands. Now, this optimization deserve a talk by themselves. And if you're curious, my talk at last WONECA was indeed about representation minimization, but I can quickly give you a perspective of their impact with this table from our paper, where the interesting part is in this row, we highlight the improvement in computation time, while in this row, we show the improvement on memory occupation. And by default, you will get the performance of the third column. Lastly, I mentioned to the literary background. So Nancy has a strong mathematical background based on the work of Anne Bullard on the UPP model and algorithms for this model. And we extended this work with some more efficient algorithms for some specific case, and by extending the toolbox with pseudo-inverse and composition. These two works are under peer review, and there are others that we are working on, where the main limitation right now is that they are conjectures that work on code, but we're still working on with the same co-authors with proving formally all the cases for which they apply. In general, as a far-reaching goal, I would like to cover all the optimizations and methods in Nancy with some formal documentation that, being the code open source, you can also formally verify by yourself. So in conclusion, Nancy is a cross-platform library that can be used for many purposes, from teaching to research to complex implementations, as a rich and flexible API model that should adapt to most network calculus work. And being open source, you can do many things, from extending it based on your specific needs to improve yourself its algorithms and explore the related research and verify the formal correctness. For documentation and many other things, there's the website that was down there the whole time. You may check it, and of course you can also ask me for any questions or help. Thank you for listening.
All right, I think we have enough time for questions.
Yeah, of course I have to ask about the FIFO leftover service curve theta parameter.
Yes.
So if you have two of them, the independent theta parameters, can you convolve them without setting the theta first? So will this both computation?
No.
Forget to repeat the question.
Oh, yes. Okay. So if I'm right, the slide. So the question was if you can compute the computation, you can compute the convolution between two of these betas without instantiating the delta before. Currently, no. There is no. So the current library only does computation in explicit way, so you cannot define formal expressions. But as I did in my own work, you can easily create functions that generate your curve, and then call, like you could have a function that that basically has this implementation, and then convolve the result with a 504, 503. I don't know if I'm being clear.
Yeah, so this function then has as input parameters all the details.
Yes.
So you can just poke around.
Yes, yes. The library by itself just computes complete representations.
Great, thank you.
You're welcome.
Quick question, how many times did it take to write this code?
Okay, the library, okay, the time was how much time did it take to write this? So this has been from my master thesis to my entire PhD work. So it's been 4 years, basically.
4 years.
Yes, it's 32 lines of code currently between the actual code, the documentation comments, and the tests. And I suppose it will only grow. Okay.
What I noticed is that you don't use units on your graphs. I mean, is there any way to impose, but if you want to use it, yeah, so
Yes.
the problem that kind of one often has, or that I run often into, is that you have a large data set of the actual data, let's be the video stream or kind of.
Don't forget that he will need to reformulate your question.
Yeah.
Just
yeah, so I'm just asking a question about using it for practically if you're dealing with large data sets. Yeah, so this is the actual traffic, and then you have to, let's say, kind of a video with you know 100, 200,000 frames, and then you have to from there on compute the envelope, and so then it becomes then the time scale at which you're working becomes a big issue, because if you're working with, you know, a continuous time scale, it doesn't work. You have to work discrete. In discrete, then the kind of, if the time scale is too fine, then it takes too long. So is that something that you can integrate, kind of to work with, kind of, let's say, a few million inputs streams and generate envelopes from there, and then apply the calculus?
Oh, yeah, okay.
Sorry for that.
No problem. Fine.
So maybe the example we're confusing on this aspect, I use integer numbers, but the library actually uses rationals. So you can use whatever granularity you want. As for parsing input with different units of measure, it's not something the library does, and I can see the problem, but it's something that you can write some other code on top of the library that handles this. The library by itself, since it supports rationals, you can put all the scales that you need. You're welcome.
So if I that seems extremely useful. Extremely useful. Being open also is very useful. Still, I have one question. Why C#?
Yes. Okay. So one of the design goals is to be easy to use. So the syntax that I've shown is should be pretty familiar from whatever language, and you don't need to know any fancy features of C# to use the library, but you write it. There are many things that are lots of useful, and for example, to handle to do the parallelization easily, and also the documentation aspects, not to mention the .NET notebooks. Many reasons for which I decided to go for this language in particular. I can give you some hints of things that to look for. So two features that are mainly useful are link, written LINQ. It's a feature of C# that enables you to basically write loops or managing lists of objects as they were similarly to an SQL query. And the benefit of this is that you can avoid allocation of lists and say before what you want to do with your list of objects before you do the computation. So yeah, I get it's complicated, but it's all hidden behind the curtain.
Maybe one short question about the same thing.
Sure.
So does this mean that C# can do lazy evaluation? Because this goes exactly in the direction of what Stefan asked. So evaluate at the end, right? Symbolically, and then evaluate.
Okay. Depending on what kind of lazy evaluation you want to do, it's more a question of software engineering than if C# can do it. I'm referring in particular to lazy evaluation of treating large collections of objects, and that is built in. So I use the built-in lazy evaluation for collections, and that helps with performance. As for lazy evaluation of NC computations, I would have to work on that. If you have any, I mean, I appreciate feedback and suggestions. So if you have some syntax that you would like to see, maybe I can do something about it.
One question in chat from David Nascimento. What was your main motivation for building a new tool rather than implementing some more features in an existing tool?
That there was none. Basically, the most complete tool is a proprietary and closed source, and it's the real-time at work library. Then there is the RTC library, which is freely available, but the source is not. So for the lacking features and bugs it has, I cannot do anything. And then there is the open source work from Stefan Bondorf that doesn't support UPP, but was based on only ultimately affine curves. So since I had to deal with non-convex curves, I needed something else.
Any more questions?
Sure.
That Nancy is a town in France, and that has a special relation with
the choice of the name may be a bad idea looking backward, but because I was looking for something that was easy to remember. And so Nancy made sense. Then I found out there's actually somebody that's called Nancy Zippo, and that's an unfortunate coincidence. But yeah, I didn't know about this coincidence when I chose this name.
Well,
another question?
Can't change the name anymore.
Yeah.
All right. Any more questions?
I have a very short question. I mean, for
Sure.
someone uninitiated. So, what is the representation of a function in your? I mean, how do you represent one function? What is it?
Oh, okay. So this part is not in the presentation, but is part of the tutorials. So for more complex functions, actually, it's better if I go forward.
The reason I'm asking is you check something like is convex. So do you check it for every rational? I don't think that's possible.
You can derive this property by the UPP property allows you to represent the function over any point of time from 0 to plus infinite, but with just a limited amount of memory. And over this limited representation, there is enough to compute the property. So
can you show the representation? I understand all your functions are ultimately
pseudo-periodic. Yes.
So can you show how you represent?
If I go to this example, okay, this would be, I would store point and segments from 0 to t plus d with the write limit excluded. So I would only store this data. Everything else is computed on request. And of course, since this information is enough to compute from 0 to plus infinite, then it also contains all the information to derive if it's convex, concave, superadditive, subadditive. Of course, the complexity changes based on the property to check, but you can.
All right, I don't see any more questions coming from the room. I don't think there are any online, and I think we are all hungry. So let's thank the speakers again.
Thank you.